distributions. What is the distribution of the sample proportion and sample mean? A sample proportion would be the proportion of some like overall population. Right? Population is really big. I want to estimate the number, or the proportion of students at Van Meter who have blonde hair. Well, that's a lot of people to ask. So maybe I pick a random 30 of them, and I record the proportion of my sample has blonde hair. So part of my sample has blonde hair. That's called the sample proportion. Sample mean, for example. Let's say I want to record the average number of siblings that students at Van Meter have. Well, that's a lot of people to ask. There's over 1,000 of them. So I take a random sample of 30 students at Van Meter and record the average number of siblings in that sample. That's the sample mean. The central limit theorem is going to tell us what distribution, the distribution of sample proportions and sample means will follow. The sampling distribution of sample proportions and sample means becomes more normal, the normal distribution, as the sample size grows, regardless of how symmetric or skewed that sampling distribution is. Central limit theorem is the theorem that guarantees that we can conduct inference on our samples. It's going to guarantee that our sampling distribution follows a normal approximation. The sampling distribution of sample proportions and sample means becomes So let's see a little bit of the central limit theorem in action. I'll pull up this applet on my television screen. And it's an applet that's going to demonstrate the central limit theorem, where I draw some candies from this candy machine. In the candy machine, I have some Reese's Pieces candies. According to the values in the applet here, 50% of them, half of them, are orange. I'm going to take out a sample, a random sample of 25 different candies, and record the proportion of them. Let's select proportion here. Divide the orange candies from everything else, and I got 48% p hat, 0.48. P hat is the sample proportion. 48% of the candies in my 25 candy sample orange. The rest were something else. It plotted that on the histogram down below. 48% with this dot right here. Let's draw another sample. Ooh, I got a lot of orange candies, 64% this time. A few more samples. 48% again. 72%, a lot of orange candies. Central limit theorem says, as I take more and more samples, the distribution of p hat, the distribution of my sample proportion, or sample mean, is going to approximate a normal distribution. As sample size grows, as I take more and more samples of candies from the candy machine, this should follow a normal model. So let's take it up a notch. Instead of taking one sample at a time, what if I do 30? Now it's going to take 30 samples and plot them on the histogram below. As the sample size grows, this should approximate a bell curve, a normal curve. Let me try 100 here. Take 100 samples, and on the histogram, it's going to plot the different p hat, the different proportion of orange candies in each of the samples on my distribution. So as the sample size grows, as I select more and more random samples from this population, as I select more and more different 25 candy samples from the candy machine, and record the sample proportion p hat, what part of my 25 candy samples were orange, it follows a normal approximation. Does that sound right? Okay. Central limit theorem is probably the most fundamental theorem in all statistics. It's the fundamental theorem that guarantees that we can do inference on different samples from the overall population. It's going to be kind of the focus of the rest of our time together for the semester. Sampling distribution follows a normal model as the sample size grows, regardless of how symmetric or skewed your population is. All right. So let's get some more information on the sampling distribution for the sample proportion. The sample proportion notation is p hat. P is the population proportion. P hat would be the sample proportion. So going back to my Reese's Pieces example on this applet, the population proportion is 50%. Half of the candies in the machine are 50%. P hat is going to be the proportion of orange candies that I take out per every one of my samples. I've got all those plotted below. The last sample, P hat was 40%, so 40% of the candies in this sample were orange. So the sampling distribution of the sample proportion, this distribution, we assume follows a normal model. But let's first make sure that's a reasonable assumption for us to check. When I describe a distribution of sample proportions, there's going to be a few conditions that make sure it's reasonable for us to assume a normal approximation applies, a normal distribution applies. I first want to check to make sure that my sample was taken randomly. Otherwise, I've skewed it somehow. I've introduced some extra bias by not following a random sample model. First thing to check, make sure it's a random sample. My sample size needs to be the right size. It can't be too big. Usually I want to make sure that my sample size is less than 10% of my overall population. Usually the population is some nationwide poll. That's not usually a hard assumption for us to make. My sample size needs to be the right size. It can't be too big, or it's no longer independent. So less than 10% of the overall population is one of the other conditions we have to check. The last condition is what's called the success-failure condition. I have to have at least 10 successes and at least 10 failures to expect for every single one of my samples. So to check the success-failure condition, multiply n times p. Take your sample size times p, the probability of success. Sample size times the probability of success needs to be more than 10. I have to have it at least 10 for my expected number of successes in the sample. Same thing with failure. N times q, the sample size, times the probability of failure. Multiply those together, it would tell me how many different failures to expect in my sample. That also needs to be more. If those three conditions are satisfied, we can assume that a normal model is a reasonable assumption for us to make. Now for this distribution, what is the average? What is the center? What is the spread? The mean of the distribution of sample proportions, the mean of p hat should be equal to p. When I go back to this candy machine, when I take 25 candies out, wouldn't I expect that half of them were orange and half of them were something else? Since 50% of the candies in the machine were orange, I'd expect when I take out candies, half of them to be orange. The expected outcome, or the average outcome for p hat, should be equal to p. The sample proportion should be the same as the population proportion on average. That's why it's kind of like the highest part of this distribution right here in the middle at 50%. But sometimes you're going to get more than you would have expected, or less than you would have expected. It's kind of like a random variable. The distribution of sample proportions behaves like a random variable. Sometimes you get more, sometimes you get less. So what's the variability from that average? We're going to describe what's called the standard deviation of p hat to talk about that variability. Standard deviation of p hat, how much variability from what we expect, is given as the square root p times q divided by n. The square root of p times q divided by n will be the variability from that expected average, from P, in our sampling distribution. All right, let's take a look at a couple examples. Let's open up those practice problems. If you have your laptop opened up, get on to Schoology. Let's just try a few different practice problems in S17 to start seeing some of this in action. Is this locked? So if I pull up the S17 practice, we should be on this document. Let's just try the first two here together in class this morning. In a large class of introductory stats students, the professor has each person toss a coin 16 times and record the proportion of their tosses that were heads. The students then report their results, and the professor plots a histogram of these several different proportions, the coin tosses that the students have done. All right, so part A here. What shape do you expect this histogram to be? Well, let's first get some data written down. What's the sample size? How many times does each person flip the coin? 16. What are P and Q? Heads and tails. 50-50. Part A, we'd expect this distribution to be symmetric. Because heads and tails, P and Q, each occur 50% of the time. Heads and tails are each equally likely to occur with the same probability. Where do you expect this histogram to be centered? What would be the middle? What proportion would be the middle? Some students are going to get a lot of heads. Some students are going to get less heads. But where would the middle be? Where would this be centered at? What would be the average of our sample proportion? What's the most likely outcome, in other words? Well, that's the number of heads. What we're talking about, proportion of heads. What part of the sample was heads? What percent would be centered at? 50%. In other words, that's asking you to find the average of the sample proportion, which is just the same thing as the overall population proportion. The average of all of our student samples should be 50%. We'd expect 50% to be the most likely outcome because you're supposed to get 50% heads and 50% tails when you flip coins. Part C asks about the variability from that average, from 50%. That's going to follow this same formula down here. How much variability should there be in this model? What's the standard deviation in P hat? That would be the square root of P times Q over N. So using the same N, P, and Q from up above. 2%, 50%, divided by 16. I get 1.125. I'd expect overall most of my sample proportions from these coin flips for my students to be about 50% or differ than that by about 12.5%. Let's talk about Part D. Part D talks about why shouldn't a normal model be used here. One of these conditions has not been met. It's not reasonable for us to assume a normal model, normal distribution for our sample proportions yet. Why not? Which condition was not satisfied? Explain why a normal model should not be used on Part D. Flipping a coin random.
Yeah.
The third one is okay. Let's just run through the first two. Then I think the third one is probably right. So flip a coin random. Yeah.
Bethany Button and Eli Kahoot, please report to the secondary office. Bethany Button, Eli Kahoot, report to the secondary office.
Are these students flipping coins less than 10% of all coins that have ever been flipped? Sure. How about the success failure condition? If I take n times p and n times q, would I expect at least 10 coins to come up heads and 10 coins to come up tails in this? So flip the coin 16 times. So 16 times 0.5. 16 times q of 0.5. Half of 16 is what? 8. I don't have enough successes and failures in my sample to assume a normal distribution applies. These are not more than 10. They're less than 10. The success failure condition is not met. I have to have an equal representation of successes and failures to make sure I have an appropriate sample. I need to have at least 10 of both. This isn't that. I don't have enough. All right, so their sample size isn't large enough. You shouldn't have them flip a coin 16 times. Let's try 25 of them. Why is 25 better than 16? 4 times. So when I take 25 times 50% and 25 times 50%, is that going to be more than 10?
Yeah.
Yeah. So now we're going to follow normal distribution. Normal model applies. Let's use the 68, 95, 99.7% rule to describe the sampling distribution for this scenario. Those numbers should sound familiar to you back when we did normal distributions from first semester. What does the 68% mean?
It's within one.
One standard deviation is 68% of all the distribution, right? In a normal model in a bell curve. 95% would be 2 of them, and 99.7 is 3. Pretty much the entire distribution is within 3 standard deviations from the average. So we're going to have n equal to 25, p equals 50%, q equals 50%. What would be the average of the proportions that came up heads? What would mu of p hat be? What proportion would I expect for my students to tell me when I flip the coin 25 times? What's the most likely response for my students to tell me what proportion of coins came up heads? 50%. The average of our sample proportion should be the same as the population proportion. You flip a coin 25 times and you get a 50% chance that they're heads. Shouldn't your average of your sample also be 50%? Of course, that's going to behave like a random variable. Sometimes you might get more than 50% of your sample of your coin tosses to be heads. Sometimes you might get less. The sampling distribution behaves like a random variable. So what's the variability from that average? That would just be the square root of P times Q over N. 50%, 50% by 25. So I get about 10%. So I would expect an average of my sample proportions to be 50% or differ than that by 10%. Let's draw a normal distribution. Centered at 50%. I'll add 1, 2, and 3 standard deviations to the left and right. What's the standard deviation worth? Standard deviation was 10%. Yeah. So 0.6, 0.7, 0.8, 4, 3, and 2, 20%. %68 of distribution is within 1 standard deviation. 95% is within 2 standard deviations. 99.7% is within 3 standard deviations. Looking at that graph, you can see that it would be pretty rare to somebody to tell me that 90% of their coin flips came up heads. It'd be pretty unlikely if somebody said only 5% of the coin flips came up heads. I guess we probably should have done part B first because it says confirm that a normal model even applies. Why did we say that 25 was better than 10? It didn't work when we had 16 coin flips. Now it works when we have 25. What condition did we kind of take care of? Third one. I would only expect 8 coin flips to come up heads when I flip it 16 times. When I do it 25 times, now that is going to be 12 and a half, more than 10. So N times P be 25 times 50%, which is 12 and a half. N times Q, which is 25 times 50% again, or 12 and a half. Both of those two numbers are greater than what? 10. My conditions for inference have been satisfied. I'd expect at least 10 successes and failures. I'd expect at least 10 coins to come up heads and tails. The coin is random. I have less than 10% of the total population, all the coin flips ever. So the normal distribution applies. Try C and D. Why don't you guys finish those two up here in a minute? And we'll put the graph up on the board for you as well. On part C, draw the same normal distribution, but we're going to increase the number of tosses for each student to 64. Draw and label the appropriate distribution model. So draw and label the same normal distribution that we had here. But we're going to change the sample size to 64 rather than 20. What differences do you see between the distribution for 25 coin tosses that we've got graphed here with the one for 64 you're going to work on right now? It'll be the same graph, but your standard deviation is going to change, right? It's still centered at the same 50%. I still expect half my coins to come up heads and half my coins to not. But the standard deviation's changed because I flipped it more times. Histogram, the verbal distribution should still be centered at 50%. I still expect a p hat of 50% because 50% of all coins come up heads. The standard deviation should be a little bit different. What did that come up to be? 6.25%? Is that right? Yes, it is. What happened to your standard deviation when you flipped it more times? 64 coin tosses as opposed to 25. Went down, right? Some point. Can you stop back in about 10 minutes when I finish up class? Draw your normal distribution. Labeled as 68, 95, 99.7%. Let's see, draw a normal curve. Label the correct distributions. 50%. Plus 0.0625 is 0.5625, obviously. Six, 8, 7, 5. Now we're going to subtract. Go to the left. 0.4375. 375. And 31.25% for the last one. Label 1, 2, and 3 standard deviations. Within one standard deviation, 68%. Within 2 should be 95. 3. Part D, what changed, what didn't between these two different models? Where are they both centered at? 0.5. What did change? Standard deviation. By flipping a coin more times, I now have less variability. There's less difference from what's expected. There's going to be less deviation from the average. I've got these two graphs kind of up on Desmos. Share the screen here. The red model was flipping a coin 25 times. The blue model, the blue normal curve, is flipping it 64 times. What do you notice between those two graphs? They're different. Different how? Which one's skinnier? Which one's skinnier? Flipping it less times or more times? 25 flips or 64 flips? More times. When I have more flips, when I increase the sample size, there's less variability from the overall average. The curve is narrower because there's less difference than what you'd expect. There's less variability from the 50% expected average. For part B, when it asks us about the differences between these two curves, the one that has 64 coin flips is narrower. By increasing the sample size, there's less variability in the expected average of 50%.
You said
Since you've got your practice pulled up, finish up the next two.